Hey folks, welcome to a new video. So in the last video we went through the code that we'll be using for benchmarking or testing as such for now, and we basically did a walkthrough for whatever every part of the code is doing, and I kept it running for a while, and I got the data that I intended to have. So both were written to this SPLICE results and SPLICE results.csv file. So two CSV files with 3 columns. In one we had the slice size. If you are not aware of the video like what we discussed, I'll add a link here. You can go ahead and check that as well before this. Cool. So we have a slice size, we have an average slice time, we have the average memory use. So 3 parameters we are taking. This is the input for now. You can have whatever inputs you want based on your benchmarking. I'm just taking the slice size as an input, and these are the outputs that we will take out to, let's say, measure or draw a conclusion from it, right? So we have the files here. If we see this, I had this code. I have this basic code to plot normal distribution and x versus y graph for whatever files you pass through it. So I just what I did was I just ran it for a while, and after 5-10 minutes it was done. So I also increased the number of trials to 100,000 or something, I think. Yeah, I increased it to 100,000. Yeah. So not the number of trials, the array size. Okay, then I just got the files here. The data I copied to the benchmark folder, and that's all. So let's try running the benchmark. So I'm in the same folder. So what I do is the code that I have here, it plots the graph and it just takes in arguments like a pair of files, and it compares whatever we pass, right? So it will be separated by commas. So I have these files and this is separated by commas, and I just run the code and I'll get the graphs, whatever there is to plot, right? So one is the smoothed time comparison. So if you directly plot the points, you will get a very haphazard sort of a thing. So I just made it a bit smoothed out, like I just made the plot to be a bit smooth. You can have a look at the code here. Like I'm not directly plotting whatever point I'm getting. I'm smoothing the curves out a bit so that we can easily spot the pattern and stuff, right? So this is for the time. So as you can see, it sort of increases, and of course it will keep on increasing as the slice size increases. In the x we have the slice size, and y is like the time taken for that operation. So it keeps on increasing, but you can see there is a consistency between both, right? So it's not like this is increasing and this suddenly decrease and whatever. So both are consistently increasing, but we can see that splice on average takes a bit more than slice, right? So that's the conclusion that you can draw from here. And for the memory, what we have is these anomalies you can ignore. Because like I said, the machine is not isolated one, the one that I'm running in. So there will be some anomalies, but what you need to see is sort of like the pattern that is formed, right? So we can see there is a straight line sort of a pattern, and there is a sharp decrease here. My assumption is this is because of like the garbage collection not kicking in. This is an anomaly because if the size increases, this should keep on increasing, but maybe there is something, it has something to do with garbage collection. I won't go much into it, but yeah, basically you are looking for a pattern. So as you can see, the memory sort of is the same that is consumed for both. So there are 1 or 2 spikes here and there, but it's sort of consistent for both, not much difference, right? So but yeah, so both are continuously increasing as we increase the number of slices, increase the slice size, right? So yeah, that's sort of a overview that we have here. Now if we go ahead and calculate the mean, median and standard deviation of there, and we plot the normal distribution graph, we get this, right? So in the normal distribution graph, what we have is this is for this is for slice, this is for splice, right? So let's look at them individually, what we can identify. So what we can see is the median and mean. Those are not that far. So that somewhat signifies that data is evenly distributed somewhat, because those are sort of close to each other. So we can expect an even distribution, which is the case here, because as you can see, it's sort of a nice normal distribution. But the next thing is the standard deviation. So this is the standard deviation for, if you compare these two lines, if you draw a straight line, this point will intersect, right? So this is the standard deviation. The blue dark lines is the standard deviation for splice, and the light ones are the standard deviation for splice. Okay. Oh, sorry, I said the opposite. This is for splice, and this is for slice. So the orange curve is the slice. This is the standard deviation for the orange curve, and the blue curve is for splice. So the dark one is the standard deviation for the blue curve, right? So here you can see from this we can measure the variability of it. So if you see the spread visually, I can tell that this width from this point to this point is less than this point to this point, right? So this seems a bit longer in general. And also if you see the value here of the standard deviation, upper and lower, and it has upper and lower, so difference like seems, that's for splice it's a bit more. So what you can conclude from that is, for this particular use case, the input affects the variability of splice more than it does for slice, right? Just I'll repeat it again. The input affects the variability of splice more than it does for slice. So the output can vary significantly for splice, but it would not be much for splice. Oh, sorry, slice. What am I saying? The output would vary significantly for splice when you compare it with slice in this case, right? It's a nice tongue twister, but yeah, whatever. So that's the use case here. So variability is more for splice, time consumption is more for splice, because as you can see the mean is towards the right for splice and not slice. For slice it's before, so average time consumed is more for splice. But another conclusion we can draw is it's sort of an even distribution, since for both the mean and median are close to each other, and sort of the difference between both is similar. This space, I mean, is sort of same between both, so the distribution is sort of similar for both. And yeah, that's the conclusion that we can draw from here. Same for memory, you can say. So there are, I'll just put it here. So there are some outliers here on the right hand side, so it's skewed towards this direction. Outliers, my guess is possibly because of these points, since like this is sort of an abnormal behavior towards the end, so this sort of curved out, that's my guess. But yeah, like that's not relevant for this use case. But let's see what we can conclude from this is same thing. This is the mean, this is the median, those are sort of close to each other, so it is also sort of evenly distributed. But the distribution is not less even than this one, right, the slice, because this gap is less, this gap is more. So that can be a comparison. For this same comparison we can do for standard deviation. This gap is more, this gap is less. So for splice the deviation is more. Same for memory like it was for time, and for splice it's a bit lesser, right? So yeah, so based on this, from our experiment, the conclusion that we can make from an efficient point of view is, for our use case or whatever environment we have run the test in, if we need to simulate a more efficient behavior, we would use slice instead of splice because of whatever reasons I mentioned, right? So this might also vary based on the conditioning that you have. I mean the conditions you are running the experiment in. Let's say in some browsers this might not hold true. Like this is the conclusion that we got from the test, but maybe let's say for some browsers they optimize for something else. Let's say Chrome optimizes for something else, Firefox does it for something else. There this might change. So yeah, it's good to run this benchmark depending on whatever conditions or whatever situations you are running in, if you need that level of precision. But yeah, this is the overall sort of general overview that would fit in like your day-to-day thing. If you want to run it, just have the file, write a quick code, compare both of them, and have the results in front of you, right? So yeah, that should be it for this video, I think. If I need to discuss something more here, I'll maybe make another video, because I wanted to sort of cover the overlap and what those mean as well. So those maybe I'll do in the next video. But from an individual standpoint, that's how I sort of run benchmarks on a very general level. Metrics I might add 1 or 2 additional metrics based on the situation, but these metrics are sort of the general metrics of if you need to run benchmark on anything and to make sense out of it, right? Variability and how the curve is uniformly distributed and like those aspects, and which is more performant than which one, like how the output might change based on the input and whatever, right? So like discussed. So yeah, that should be it for this video. If you found it helpful, please drop a like, share it with your friends, and comment if you want me to make videos on something else. And yeah, if you have any suggestions, feel free to drop a comment, and if you think I can improve on something else, of course, like sure. And yeah, that should be it for this video, folks. See you in the next video. Bye.